Okay, so let's start our lecture today. So, um, yeah, so actually last time when yeah my phone dies off last time. So yeah, uh, yeah, sorry about that. And then um, yeah, I was left with a case where actually I show that. So yeah, so actually if you compute like the points with the same distance, but they with different angles. So for example, if you take let's say that you have the point. Let's use the A12 to denote this point with the real coordinate as 1 and imaginary part as like 2i. And then this is the point. So there are eight kind of points, right? So this is the B21, so, right? And sorry, this is A21. I use the same letter A for here. And then I use maybe I use the letter, let's say B for the second quadrant, -1, 2 for this point, and then let's say this is equal to B -2, 1, and then this is a point, let's call it C of -2, -1, and then, yeah, sorry, I did something with that. So C of -1, -2, and then so this is C of -2, sorry, -1, -2 here, and then this is this is letter D here. So this is 1. Okay, so 2, -1. Okay, so yeah, so remember that we are calculating like the sums over 1 over like the value squared, right? Yeah. So the letters yeah. So it's not very good. Yeah, good notation. So. Like the letters, sum over like the ABCDs. Okay. Okay. So sum over the 8s. Okay. Maybe AIJ or something. Okay. The IJ is like vary between these 1 and 2s, and also the -1, -2s. Okay. So here, yeah. So here, what we do is that, yeah. So we calculate for angle theta, right? So remember that there is because each of it is like r into the I theta, right? And then when we plot this, there is like a 1 over r squared. And then there is various thetas. So so here I'm using, remember that I use this theta, and then this is like pi minus pi over 2 minus theta, and so on and so forth. Okay, so so r into the I theta here. Okay, so yeah, so this is pi over 2 plus theta. This is pi minus theta. Pi, sorry. Yeah, I try to make like state again for the computation. Okay, 3 pi over 2 minus theta. 3 pi over 2 plus theta, and also here this is pi minus theta. Or just minus theta. Okay, just minus theta. Okay. Okay, so here when we are trying to do the computation here, okay, so here this is like a okay, so first we square it, right? So it becomes e to the 2I theta and then minus. Okay, so this is the first point. And then for the second point, what we do is that second point we square it, and then we take the negation, right? Pi minus 2 theta, so 2 theta minus pi, right? And then the next one is e to the pi plus 2 theta and then minus. And then so this is equal to so here this is e to the, so for this point it should be 2 pi minus 2 theta, right? And then take the negation. It should be 2 theta minus 2 pi, right? And then plus another point. So this is 2 theta minus 2 theta minus 2 pi, right? And then for the next point, so it is 2 theta minus 3 pi, right? And then plus minus 3 pi, maybe minus 2 theta minus 3 pi, and then plus e to the 2 theta, the I 2 theta. Okay. Yeah. So when you let's try to compute this one. So okay. So here, so we have negative 2I theta, and then there's another negative I 2 theta here, right? Because and then this is 2 pi I they cancel out. And then you have the negative 2, so positive 2 theta minus I. And then this is negative 2 theta minus I. Okay, so here there's an, oh, this is just 2 pi, right? Okay, so this one cancels out with this one, right? So because it's going to cancel out. And here, okay, so this is e to the I 2 theta minus pi, right? So minus pi e to the I theta minus e to I 2 theta minus pi. So this can come with this one. Okay, and then this one. So this one is just the e to the negative I pi. So this is e to the negative I 2 theta minus I pi, right? So e to the negative I e to the negative I 2 theta minus I pi. So yeah. Yeah, so you see that these points, they all cancel out based on, yeah, so this point, they all cancel out. Oh, my bad. So actually, yeah, I didn't include all the formula here. Okay, that should be good. Okay, sorry about that. So, okay, so yeah, you see that like as long as you have all the possible like as long as these numbers they are not the same in this situation. Okay, again in this situation, so as long as these two index number of the points are not exactly the same, then 1 over that guy's square will be cancelled out eventually. Okay, so what's that? So remember, like we talked about loops last time, right? So for a loop of length, let's say 1, right? So again, so this point they all lies on the loop of length 2, right? Because the biggest one it has wait. Yeah, so they all lies in the loop of length 2. Okay, so these are points, and then however we calculated last time that the loop of length 1, the corner points doesn't cancel out, right? And then also I think the yeah, and also I think the point that are lies on this axis, they are not cancelled. I think the rest points, right? So if you think of the rest point, I think they are all cancelled out somehow. Because if you draw any right, so if you draw any squares, you draw the squares like that, and then so I'm trying to draw a 4x4 square, but somehow it's like very awkward because it should go inside. Okay, just imagine that this is only the fourth quadrant, right? So imagine that this point kind of lies on the y-axis. Sorry, on the imaginary axis. Okay, and then this point lies on the distance 4 away from the imaginary axis, and then you imagine that here this one kind of lies on the real axis. Okay. So if so for these points, yeah. So for these points, if I take away, okay, so it should be in all the quadrants, right? It should be yeah. So it should lies in it should be extended like here, right? So it should be. So I'm just drawing things in the first quadrant, but you may imagine that this guy there is also things that lies in the first quadrant, and then in the second quadrant, in the third quadrant, yeah. So it should be like a complete square like that, and then there after you delete the corner, like after you delete this corner, and this corner here, and this corner here, and this corner here, and also you delete the one that lies on the real and imaginary axis. So there's one on the real axis here, there's one on the imaginary axis here, and then there's also maybe another one on this point here, which I didn't draw, and then another point like here. So after you delete them, so what's left is exactly, you see that in this case, okay, in this specific case, there is only 2 points that lies on each, let's say, segment. Okay, I call it a segment because, and then there is a total 8 pieces of segment, right? So here there's a segment that contains 2 points. Here there's another segment that contains these 2 points, and then there's another. It should be another one here, and another one that's here, another one here, another one here, another one here, another one here. So there's a total eight. So totally. So I think this is more for general, right? So for any square. So for square, I mean like this loop. Okay. So for any, in a square loop. Okay, so I use the square. Okay, so here of length, let's say bigger than 1. Okay, so on 1 there's just there's no inside, right? So it's just one on the corner and on the axis. So there's nothing else. So of length bigger than 1, so the all the points that lies on the segments. Okay. So by segments, what I mean is just this circle like points. They are totally, for each of the there are exactly 8 segments. Like the point that lies on the segment will be cancelled out. Will be cancelled out via the taking the taking the sums. Yeah, so we are taking the sum. Okay. Okay. Yeah, I think that's a very bad mistake. Let me think of okay, so maybe let's say n, okay, bigger than 1. Okay. So okay, and then maybe I can use this okay, so maybe let's use the letter because here let's start with this length first. Okay. So an, so again, so so if I look at the segment here, it should be suppose we are in the general case. Okay, so we will look at the segment here. It should be length n, right? And then comma what? Comma. Okay, so now for this one, I can let the index run, right? So I can run it like 1, 2 for this n equal to 2 case, and then I can run to like 1, 2, 3, 4, 5 for like n equal to, let's say, 7 case, right? So yeah, so as long as it's bigger than 5, that's fine, right? Bigger than 5, I think. Yeah, so this is wait, so in this case, this n is actually yeah, I think, sorry, my bad. So this n is what? This n is 4, right? Yeah, so this n is 4. So yeah, bigger than 5. Because this n is 4, so I can only sum 1, 2. Oh, this I, j. Yeah, so I can only sum, so in this case, okay. If it's 2, then let me get sum 1. So this is 1, 2, wait. This is 2, 1, 2, 3. This equal to 2. Oh, n equal to 2, there are 3 points, okay. And and then n equal to 3, there are 1, 2, 3, 4, 4 points. Okay. 1, 2, 3, 4. Okay, so in this case, actually, okay, my bad. So in this case, actually, n equal to 3. Okay. Yes. So it should be n equal to 3. Then there are 2 points. Like you can sum for each line segment. Okay. So yeah, because this distance, right? So if you count it, it will be 1, 2, 3. So in this case, n equal to 3. Okay. Sorry about that. Okay. And then you have a n's. Okay, so I. So where this I goes from 1 to 1 to n, right? Yes. Because the number of points is 1 bigger than the number of points, right? So for first point you said 1, second point you said 2, and yeah, you can do the corner points. Sorry, n minus 1. What I mean is, I think what I mean, n minus 1. Yeah. Because the height here is 2, right? Okay. And then you sum over the ABCDs. Okay. Okay, let me use another letter. Yeah, so, okay, let me use this, okay. And then I switch the index. So now it becomes I, comma, n right, squared. Okay, and then 1 over b, and then it's the same thing, right? So yeah. So yeah, I will repair it. And b something like square plus, and then all the way it should be 1 over like a d something square plus. Yeah, I'll just do that. Okay. Okay, so eventually it will be cancelled out. Okay, eventually it will be cancelled out. Okay. Okay, so here okay, so here, okay, so the only thing left, is the corner points, plus the point that lies on the axis. So yeah, so let me try to think. So then, okay, so remember that we are talking about the summation over omega 1 of omega squared, where omega not equal to 0. So this one is, yeah, so we are indexing by the loop order, right? So we start 0, and here we like 1 here, 2 here, 3 here, 4 here, 5 here, 6 here, 7 here, 8 here. Yeah, so we're going around like that. So let's say why are we? So what is the next step? So okay. Oh, yeah, so this omega is not equal to 0. So, okay, so okay, so let's do that. Let's pull the omega 1 front, and then let's do the sum. So, so I'm assuming that there's like a natural index. Okay, so so I'm indexing it by like let's say that this is omega 1, and then this is omega 2. This point is omega 2, and then omega 3, omega 4, omega 5, omega 6, omega 7, omega 8, omega 9, and then we do like clockwise. Okay. Okay, so let's see what are these equal to. So okay, I don't think it's good to think about like that. So I think it's good to think about in the case where yeah, maybe let's just start with the 4 points. Yeah, so let's just start with the 4 points here. Okay, so remember that we are summing over let's just let the n to be the amount of loop, the loop length, right? And then we for each loop there is only 8 points that matters, right? So it's a point that lies on the axis plus the 4 corner points, right? So so how will we calculate the point that lies on the axis? Okay, so here, this omega 1, it is exactly okay, so so this is like n comma 0, right? Just the real number n, okay, just the real number. So then when you take that, it just be 1 over n squared, okay. And the same thing for this one. So this one is exactly negative n, okay. So this is, when you square it will be exactly 2 over n squared. And then this point. Okay, so this point is exactly what? Wait. I think I'm kind of misdirected by the drawing. Okay, so okay, again, this omega 1 and omega 2, they yeah, even though we are assuming that they are outside the origin, but they may not be the equal length. Okay, so this graph is actually this lattice may not be a square lattice. Yeah, I think that's the point that I kind of somehow misguiding here. So, but I think this idea still works, right? So, for example, you may have the omega 1 longer, and then yeah, you just increase the step size by some let me think. Oh no, actually, I don't think the idea will still work. Because as long as this omega 1 and omega 2 they are not the same length, then this point cannot be identified with this point, right? Because this is measured in the omega 2 sense. Yeah, so this so bad here. Okay, so yeah, it's a very misleading. Sorry, it's a very misleading. So is there something else I can do with the is there something else I can do? So I think if they're equal, then I can definitely show that, right? Okay, so maybe let's just add the condition that omega 1 equal to 1, omega 2 equal to I. Okay, so then this argument is true, okay? So, yeah. So, okay, so, I think the case is that, okay, so let's just finish this case, this one first, and then let's see what we can do about the other case. Yeah, it's just like cheating a little bit, okay. So, yeah, and then we have the I term, right? We have the in square. Oh shoot. Okay, so this is in, and then negative in. So when we square it, we get actually these two cancel out. Okay. Or don't they? It's 1 over omega squared. Okay. Yeah, so 1 over. Yeah, so they cancel out. Okay. And then you have the corner points. Okay. Okay, I think use the square root of 2, right? Yeah, so the length is like square root of 2 times n, right? Times, so this is the radius, okay. Well, this is 1 over r squared, okay, times into the negative I theta and then you have I think it's 2 trillion here, so theta. No. So yeah, so this theta is like 1, 2, 3. negative 2 theta minus 2 pi. Okay. So it's just negative theta. So they cancel out. Okay. Okay, so okay, so oh, okay, I see. Okay. Okay, so yeah, so they all cancel out eventually. Okay, and then okay, so then that's yeah, so yeah, so okay, so I think you can come up with an argument that because for a large, right? So then because for a large, this radius is large, right? So because for any point, let's say because all the finite loop, they all eventually cancel out. Okay, so maybe let's worry about like the I think there might be the worry about some alternating, like, right, because the value will be only cancelled out after a complete loop, right? So maybe then you may wonder, okay, maybe what happens between like if the loop is not finished, then the value may not be equal to 0. Then how do we guarantee the convergence? So I think the idea is that even though the value may not be equal to 0 before you complete the loop toward the final stage, but remember we are taking like the 1 over this some radius times the e to the I theta squared, right? And then because when this n is getting larger and larger, this radius is getting larger and larger. So eventually yeah, but you have to take into the consideration of the points. So right, so but but yeah, but the point is grows like 1 over n, right? Yeah, so yeah, so for the convergence, So yeah, so how do I really show that? So we have the summation yeah, I think I remember that if I have a loop that's really large, yeah, so I have a loop of this n, the how many points are there for each loop. Okay, so yeah, because I want to evaluate the the ratio. Okay, so what is the maximum band I can get for a loop of length n? It has how many points? Here you have one. Okay, so for each of the side, right? So for each of these segments, you're having one. So for each of the sides, you are having m plus 1, right? And then it times 8. Right, there are totally 8 line segments. But then you want to subtract because this the axis, the intersection point on the axis and also the intersection point on the corner are counted twice. So there is minus 8 for corner point and for axis intersection points. They are counted twice, so minus 8, which is exactly 8 endpoints. Okay. It has 8 endpoints. And then okay. Okay, so right, so so how does this argument works? And for each of the points, so okay, so yeah, so I want to say that so for each point, what do I want to show? Okay. Okay, so in this case, I want to show that the sum is actually 0. Okay, so for each of so then I want to show that. So I want to show that for n being large, right? So all the sums minus 0 is less than epsilon. Yeah. So this is what I'm trying to show. Okay. So let me try to think. So y is true. So minus 0 basically means that just taking their sums, right? So this final sum, the modulus of the sum is less than epsilon. Okay, so I want to show that the modulus of the sum is less than epsilon for any. So you just start at any point. Okay, so like pick a time where I stop. Okay, so like you're running like a loop, and then if I start at any point, then the sum from the beginning to this point must be less than epsilon. Okay, so this is the thing I want to show. Okay, so the reason why it's less than epsilon because so for the sum, right? So if you fix an n, the sum of the points on the n. So how do I index the point on the n? So how do I index the point on the n? Okay, maybe I use the number omega ni. Okay, so I from, let's say, 1 to 8n. Okay. I'm not like okay. Yeah. So because there are totally 8n points on the loop of this n, so I'll just say that it's go from 1 to 8n. Okay, exactly 8n points. Okay. Yeah, maybe I'm abusing some notation. Okay. And then this is equal to okay. So yeah. So 1 over modulus 1 over this one square is less than. Okay, so the modulus of this one square, of course, is less than equal to, you take the sum of the modulus, right? Okay. Yeah, so the modulus is taken over the bottom. Okay, so this one is, again, I'm using a lower bound for the denominator, which is, so we will just use the notion n here, right? Where n is like the loop length. Okay, so because the smallest radius, the smallest one, the smallest radius is exactly this point. All the point has bigger radius. The smaller radius is here, and this has length n. So we have 8n times 1 over n squared. Okay, so which is equal to 8 over n. Okay, so the modulus is less than 8 over n. So for definitely speaking, for n large, this is very close to the close to 0. Okay, so we are allowed to do that. Okay, so therefore this shows the convergence, right? So because so basically you can argue that yeah, so basically you can break the indices into 2 parts. So one part is the loop indices, right? So basically for any epsilon, right? So you can say that you can always find such loop, right? So such that for any loop that has length bigger than this one, then no matter where you stop, no matter where your sum stops, the distance of this whatever the stop sums it has distance less than epsilon to the origin. Okay, has distance origin to the origin, and then it may happen. Okay, so what happened before this loop starts? Because before this loop starts, all the previous loop contribute to 0, right? So you just like some part of this loop, yeah. So that gives the proof of why it converges. So okay, so then maybe so then like you may wonder, okay, so what happens if this omega 1 and omega 2 is not so nice, right? I think this argument will still work, right? Because yeah, I think this argument will still work because I'm picking the theta so that, so yeah, you may imagine that this, okay, so you may imagine that even though the ratio of this omega 1 omega 2 may not be this nice, like 1 and I, so but I think this corner point idea will still work because just imagine that this is theta and then pi minus theta, right? So we are taking theta to be somewhere here, and then this you do the symmetry around the imagined axis, and then you will always get pi minus theta, right? And then you do the symmetry around the real axis, you will also get the pi plus theta, right? And then you'll get minus theta. So I think this argument will work. Okay, I think the corner argument still works. But the thing is that what happened to this argument, right? So this very important argument, let's see, would it still work here? So let me try to think here. We are under the assumption that, let's say case 2, this is case 1. So case 2, if omega 1 is equal to 2, omega 2 is equal to I. Okay. So here, I think the corner argument will still work here. Okay. So then this is a rectangle of type 1, 1, right? So this is like a so type 1, 1. So right. So so this argument so this argument will still work. So okay. So so the corner point argument, okay. Would still work, okay. So, but I think there might be a little bit trouble with the so with yeah, so might be some trouble with. Oh, okay. Oh, actually, okay. Yeah, so there might be some trouble with this part. Okay. But let me focus on this part. Okay, I think this part is the main, is a very important part. So, oh, I see. So, I think there's no issue with this part even, because why? Okay. I think the idea is that I can always break these 8 points. Remember, like we have a calculation for the 8 points. Okay. I think we can, because here, right? So if you think about that, wait, what am I thinking about? Okay, so let me actually draw another picture here. Okay, let me actually draw another picture. So let's try to do n equal to 2 case. Okay. So yeah, so convergence. Yeah, we're done with the first case. So okay, so maybe let's leave that. Okay. So here, let me do a. Yeah, it's very hard to draw, I think. So here we have this, that, okay. And then we have another copy, here another copy. Okay, so it's the loop 2. So, okay. Okay. Okay, so there are so a equal to 2. So right, so these are square here. Oh, so these are rectangle here right now. Okay. Oops, I think I can draw like the portion. Okay, so let me draw that. Yeah, it looks like different lengths, but yeah, it's a little bit awkward here. So okay, so yeah, so suppose that these are all equal. Okay. Okay, so here, okay, so look at these 4 points. 1, 2, 3, 4. Right. So this forms exactly the same structure as this one. Okay. So same radius, and the angle cancel out. Okay. So these 4 points being cancelled out, and also these 4 points. Okay. Also, it's share the same type. So I strongly yes. So they are exactly the same point, because you think of this angle. Okay. Yeah, so this angle is theta, suppose that theta, then pi minus theta, right? And then this one. Okay, so they cancel out. Okay, so even though the radius is now the same length, even though this omega 1 and omega 2, they are now having the same modulus, but this argument will still work. Okay. And then for this argument, I think we just pick the yeah, so you just change it to whatever the minimum of this omega 1, omega 2, right? Yeah, so maybe you add like n times the minimum between omega, the minimum among the modulus of omega 1 and modulus of omega 2, okay? So here maybe I just write, because here this omega 1 has less modulus, so sorry, here omega 2 has less modulus. Yeah, so either omega 2 or omega 1, like minimum, yeah. So eventually very small, okay. Okay, so then you may wonder like, okay, so, I think there is still one scenario that we didn't talk about yet. So I think that's the case where, yeah, I shouldn't be so fast. Okay, so I think that's the case where you have this scenario, right? Yeah, so the things that's on the border. No. I think the thing on the axis is kind of bothering here, so let me try to think. Okay, but I don't think that's a big issue, but I think the limit just may not equal to 0. Okay, but instead I think it just equal to whatever the access point converges to. Okay, and I think because yeah, I don't think it converged. Wait, does it? Yeah, so I have to analyze this one. Okay, so yeah, I think last time I made a mistake by computing quantum points. I think I somehow take the square first and then I take the minus sign. So which should be in the opposite direction. So I think it should, no. I think I take the minus first and then take the square. In which I should take the square first and take the minus. I think that makes a very big difference here. Yeah. So. Yeah. Okay, so the let's focus on the okay, so access point. So for the access point, does they converge? Okay. Okay. I think it will converge because you are taking the number of loops, right? And then for each of the loop, the exit point is actually has power -2, right? So the growth rate is like -2 power. So so here you will have so let's make it slightly more general here. So here we are. So actually, I think these two actually doesn't matter. So okay, so let's say that this omega 1 is in real is in real number. Okay, real plus. Okay, real plus, and then this omega 2 is actually in this I real plus. Okay, so then so 1 over. So I won't bother with omega 1 here. Okay. Again, I'm building notation about a little bit. I'm saying like because originally in the original sequence there is like omega 1 over sum of the omega not equal to 0 or omega 1 over omega 2 squared. Yeah. So I'm using this omega 1. Oh, actually they should be the same omega 1. Okay, they should be the same omega 1. So I'm not building notation. Okay. So when this omega 1 okay, so the sum becomes okay, so what I'm drawing here. So yeah, so there should be, yeah, okay. Oh, there is actually a point here. Okay. Yes. So sum over n omega 1 squared. Yeah, so this is this point. Okay. And then times the other endpoint, right? So the other endpoint after squared, they have the same value. Okay. So and then plus. So now you have n times some imaginary numbers, right? Okay. Yeah, so what should I write? So maybe I write I times n times the modulus of omega 2, okay, squared. And then 2 copies of them. Okay. Yeah, so again, this one. So you can comfortably pull out like a 1 over n squared times some constant. So here is a real number here, and then minus 1 over modulus of omega 2 squared. Okay. So it is convergence. Okay. So okay, so Okay, so again, if I want to show the limit actually converges to a point, so yeah, so if you want to argue that the limit actually converges to the point, so that this limit to be equal to k. Okay, so we conclude that this actually converges to this number k. So yeah, so I think what we can do is that so this sequence, if we just look at this sequence itself, it converges to k without any doubt. So so why the original sequence actually converges to k? Because for large n, okay, so we can pick, so fix epsilon bigger than 0, we can pick large n such that this minus the yeah, so fix n, fix epsilon bigger than 0. So so there is n such that yeah, so such that summation n from 1 to n of 2 over x squared times dy minus k is less than epsilon over 2, let's say. And then we can also pick, so this argument kicks in, right? So yeah, so this argument will kick in. So for n large, we know that the modulus is always less than, because the thing is that the rest points, they are all cancelled out, okay. And then besides these 4 corner points, so yes, so here I should modify this argument by slightly a little bit. So what should I do? So so what should I do? Oh, okay, so actually this argument has nothing to do with the cancellation. It's just like a argument about yeah, so this argument has nothing to do with cancellation. It's just like you find a lower bound for the smallest by the smaller radius. You find a lower bound of the distance, and then that gives the upper bound for the 1 over the modulus. Okay, and then that gives the upper bound for the modulus of the sums. Okay, so because yeah, so what should the argument be? I want to say that all the okay, so this is counted in terms of loops, right? So A is like the number of loops, right? So Okay, so yeah, so this argument would also work for loops that are yeah, so for loops of length n, then the total so not the total, but if you stop at anywhere, like you fix a loop of length n, if you stop anywhere, then I start to take the sum. Then this argument is saying that that sum can be is at most this part away. It can be anything bigger than this distance away from the origin. Okay, so this is what this argument is saying. So yeah, so okay, so here I want it to be, so for n large, okay, maybe let's say bigger than n2, then I want to say that this is I want to say that this is less than epsilon over 2. Okay. So now it picks the n1, n2 that is big. That is bigger than this n1. Okay, so this is called n1. So then for n bigger than okay. For n bigger than n1. Okay. So then for n bigger than the maximum over n1 and 2, then we have that okay, so let's change it for safer choice. Okay, let's change it to n1 plus 1. Okay. Yeah. So why is it true? Because for any n bigger than this, because okay, so this n bigger than n1 plus 1 means what? So this n bigger than this n1 plus 1. So remember that. Actually, because remember that I'm talking about the loops, right? So yeah. So if you like if you think of any like because originally our sum is not indexed by loops. So our sum is not so this is just loop index, right? So we are just talking about the loop 1, loop 2, loop 3. I mean, it's convenient to talk about the sum in terms of loops, but what really we're doing is that we are summing over like the small little points, right? We are summing over the small little points that are on the loops, that are on the loops. So what we do is that so for any, okay, let's say So maybe we will find out, we want to find a way to convert this argument, this loop argument to the actual point argument, right? Because so we want to find the index. Okay, so so for the point index, so basically the idea is that okay, any point either on or after the nth loop. Okay. Has total sum epsilon close to k. Okay, so why? Because for any point after the nth loop, suppose that it must have so either it's on the nth loop or it's on the some larger loop, right? So from larger loop, then we can break into two cases, right? So one case is like the sum consists of two parts, right? So one part is the loop part. Another part is the whole loop, and the spare part is like the points that's remainder. That's not a whole loop. That's just some remaining part, right? It's a whole loop part and the remaining part, right? So the whole sum, okay. So the whole sum is actually breaks down into two parts. Yeah, so the whole part actually breaks down into two parts. So sum is actually breaks into two parts. One part is the loop part. Yeah, it's like the taking over the whole loop, right? Because we can always find a closed loop that contains it, that's contained in the sum, as one part of the sum, okay? And then plus the spare part, okay? Or the remainder part. And then we know that for this for this point after the nth loop, the whole loop part, okay, is if it's on the nth loop, right? So then the loop part is like n-1, right? So then this n-1 is some number bigger than this n1, right? So then we know that the loop part is at least epsilon over 2 close to k, right? So this loop part is epsilon over 2 close to k. And then we know that remaining part is what? Remaining part is is small. It's it just less than epsilon over 2. Yeah. So therefore So therefore this. So you can think about like this whole sum minus k is equal to this sum minus k, because this sum is equal to this plus that, right? So this sum minus k is equal to this one minus k plus just the remaining one, and then by the triangle inequality, this one, because the whole modulus is less than or equal to this modulus, which is epsilon 2, and then this one is less than epsilon 2. Okay, so that's the whole argument here. Okay, so so we will continue with the more general case, right? So still, this is the case. This is we assume that this omega 1 is like some positive number, and omega 2 is some I, like a real like positive number, I times one positive number. So we will talk about the more general case. Okay, next time. Okay.